Hello friends, welcome back to my channel Hangover Theories. In this video we are going to discuss about Maxwell laws as I promised, and I also said we should be knowing about electric field and magnetic field, at least some basics, right? Then only we can understand Maxwell laws and Maxwell equations. We can even read the equations. Let's get into the story. Let's first discuss about electric field, and let's say there is a charge over here, and this charge will be spreading some field around it, and this is called electric field. These are the electric field lines. These lines represent the electric field, so it will spill out from the charge. These arrow marks represent electric field density. Okay, to understand clearly about electric field, let's take some situation. This is the situation where we're considering a switchboard, just a socket in it, and the switch is off, and obviously we know phase wire and neutral wire and the ground wire will be running out of the socket, and the ground wire will be turned, and phase and neutral will be taken to the supply. Now my question is, what happens if I put finger into the socket? Will I get shock? Just think of. And the answer is no. That's very simple, right? Because the switch is not on, switch is off. But my question is, though the switch is off, there will be electrons all the way from the socket to the supply. Okay, so this is also made of copper, and this also will be having some electrons, right? So when you put the fingers into the socket, there are electrons all the way, and they have some charge, and you are attuned yourself, but still you are not getting shocked. Your common sense is, bro, the switch is off. The answer is, there won't be any kind of excitation from the supply to the electrons in the wires. Now let's move on to the other case where the switch is on. This is the switch on case, and you can say the switch is on here. When the switch is on, there will be some excitation from the supply. That means all the electrons in the wires will get some excitation from the supply. They will be pushed from the back side. So the supply will push all the electrons. Okay, electrons, move front, move front, move front. But the electrons can't spill out from the sockets, right? Until and unless I connect any load. Then only the circuit will be shorted and the electrons will flow through the load which I connect. So let's take one load. This load can be your iron box, your freezer, AC, any electrical thing, and even you. And simply I can say the excitation which the supply is giving, or the force with which it is pushing the electron, that force I can call as EMF, electromotive force, simply. So now the electron starts running from the socket to the load. So let's do that. There is movement in the electrons, so that I can say the charge is flowing, and you know the flow of charge is nothing but the current. So here I have current. When the charge is moving, a magnetic field will be generated around that wire. The direction of the magnetic field depends on the direction of current. We know we will be using some thumb rule, right hand thumb rule. This is the magnetic field. So I can simply say, when the charge is moving, then only we can get the magnetic field. When the charge is stationary, sitting, idle, but excited, then it will be having electric field. When the same charge is moving, it will have magnetic field generated, and also since it is a charge and it is being excited, it also have electric field. So when I consider a current carrying conductor, there is a magnetic field around it. So in this case, you will be having both electric field and magnetic field around the wire, and collectively I can say there is an electromagnetic wave around the wire, right? This is how we are getting electromagnetic wave. But why doesn't this electromagnetic wave affect us? And we know our household voltage will be having 50 hertz. The voltage we get is having 50 hertz, and the current produced by the voltage source will be also of 50 hertz, and because of this we will be getting electromagnetic wave, which is also have a frequency of 50 hertz. And this 50 hertz electromagnetic wave can't do anything to our body. Waves which are having very high frequency, which we usually use for the mobile communication, which is of gigahertz, 3 to 300 gigahertz. So that high frequency will affect you, but this 50 hertz doesn't. It doesn't have much power to affect you. So let's move on to the main thing of the video, that is reading the Maxwell equations. In the first figure, you can see electric field coming out of the electric charge, and I have shown this using the arrow marks. And in the second figure, this cross mark at the center represents a current carrying conductor which is poked into the screen, and around this current wire we will be having magnetic field which is generated, right? And this magnetic field direction will be taken using the right hand thumb rule. Now let's start how to read the Maxwell equation. Before answering the Maxwell equations down there, let's go through a scenario where you are moving along the path of electric field away from the charge. By the common sense, you can simply say as you move away from the charge, the density or the strength of the electric field will decrease. Simply, if the density is d1 here and density is d2 here, obviously you can say d1 will be greater than d2, since the second point is farther away from the charge than the first point, right? Now let's read the equation. Del represents change and dot represents the direction you have taken. Change of field density when you are traveling along the D path or traveling along the electric field path. So that's the same case we discussed. As you are moving away from the charge and in its direction, in the same direction of E field, you are experiencing some change as you move away from the charge, and it will be the charge density, volume charge density rho v. We will be talking about this later, and how to read the second equation. And before going that, let's take another scenario. Let's measure densities at these points, and the main thing is all these points are exactly at the same distance from the center. You can simply assume a circle. Now I am measuring the E field traveling in this direction. All the points which I am joining here, at these points the electric field strength will be same, because every point is situated at exactly the same distance from the charge, and this is called equipotential surface. Any point on this surface will have the same strength, just because any point on this circle will be exactly at the same distance from the center, which is nothing but the charge. As I move on this path, I am not experiencing any change. At any point the strength is same, because every point is exactly at the same distance from the center. Change of field strength while you are traveling in the perpendicular direction of the E field. If this is the direction of the E field, obviously it will be the perpendicular direction of E field. And when you are traveling in that direction, are you getting any change? No, simply zero. That's it. Done with the first two. What about next? In the same way, when I am traveling in the same direction of B, so this is the direction of B, and I am calculating the B along this path, traveling in the same B's path. So the change of field strength when I am traveling in its direction, when I am traveling in the B's direction, and initially it is a circle, and every point on the circle will be exactly at the same distance from the center, nothing but the wire, and I will experience the same B. I won't be having any change. Change of B when I am traveling in its direction is 0. Simple. Change of B when I am traveling perpendicular to the B's direction. If this is the B's direction, this will be the perpendicular direction of the B. When you move along this path, will there be any change in B? Obviously, when you're traveling in this path, that means you are traveling away from the wire. When you are moving away from the charge, electric field is being diluted. When you are moving away from the wire, the magnetic field will get diluted. So there will be some change. So the change is nothing but the current density. And here actually you have to take magnetic field intensity. So the basic difference between B and H or D and E is nothing but the permittivity, the medium. So this is how we have to read the Maxwell equations. I hope you all got this. I want to end up this video with a lame question. So I already discussed that our household voltage will be having 50 hertz, 230 volts or 220 volts ranging, and obviously the current which this voltage generates is also of 50 hertz, and obviously the electromagnetic wave around the wire will also be of 50 hertz, right? Now what if I want to transmit this 50 hertz signal into the space? And the basic thing is, for transmission we need an antenna. My question is, will we be able to transmit this 50 hertz electromagnetic wave into the space using an antenna? Is it possible or not? That's my question. And I already said I will be ending this video with a question, and you will be finding its answer in the next video. Like, share and subscribe only if you like this video. Thank you very much.